welcome back to the shop. Right now I'm using my early Christmas gift from my wife, and I have a new video camera, a new Canon video camera we're going to be using. It's a Vixia HFR62, and I got it because we're able to control it remotely, and I'm also able to add external mics and stuff on it. So we're going to be trying this out. I still have my regular video camera I was using before, which is a older Panasonic HCV 500, and it still works fine. Just the battery's starting to kind of fade out a little bit, and the focus motor is starting to get a little noisy. So now we can use both of them in conjunction and kind of get multiple shots, multiple angles of some things. So getting on today's video, what we're going to be doing, or a project I'm going to be working on, is we're going to be making an ER40 collet chuck for the Southbend lathe. Now I have a set of collets here that I picked up. We did some Cyber Monday shopping, and I got it set from Shaw's. It's a set of 5 from, I believe it's 3/8, what is it, 3/4, I think it's 3/8. Yeah, from 5/16. From 5/16 to 1 inch in 16ths. So we have 6 collets here, and it kind of crosses through with the 3C collet set that I have. Now the 3Cs, the problem with 3Cs is they only go up to 1/2 inch. Even though I only have a 3/4 inch through hole in the spindle of this lathe, 3C collets only go up to 1/2 inch. And the other problem is you don't get a wide gripping range. You're only about plus or minus 10/1000ths of the stated size on that collet. So you need a lot of them. So I mean, you need 32 collets to span from the smallest to 1/2 inch to be able to get all the sizes in there. Now ER collets, on the other hand, have a little bit of a wider range of gripping, and they go up higher. Their highest, the highest they go is 1 inch, which is this one here. So we're going to be making a collet chuck for this. So now, unfortunately, I had ordered the stock for it, but unfortunately didn't make it for this weekend. But we still have plenty of material to go through, and what we have to do, what I also ordered with these, is the spanner wrench for the collet nut, and the collet nut here, also from Shaw's. And there's a reason why we ordered this. Now you can make your own, but there is a little kind of ejector feature to this. There's a little, and we'll get a closer shot of this. There's a little, it's basically like one thread, and it catches this lip and allows you to eject the collet. So, and there's also a taper, I believe it's 30-degree taper on the tip of this. So, I mean, you can make it, and you can do it. It's just going to take a little bit. It's also going to be threaded. So this is already threaded. And the problem with this is it's metric. It's an M50 by 1.5 thread. So now we got an issue. I have an Imperial lathe. How are we going to cut a metric thread? Well, simplest and easiest way to cut a metric thread on an Imperial lathe is to get a die. Well, an M50 by 1.5 die, the only one that I could find that was the cheapest one I could find is $100. Not happening. Now the other option is to get a metric transposing set. So if you guys watch Adam Booth's video, he showed a set that was made by somebody, donated to him, which he then gave away through picking names out of a hat. So what that does is that basically a combination of gears, and we'll go through all this on the table, slows down the lathe to allow you to cut metric threads, changes your gear range on your gearbox to allow you to cut metric threads. Well, those are very expensive and hard to come by. So we have 2 options that we can do, and both are with change gears that come with a 9C or 9B. So these are relatively readily available, and I actually happen to have a set because this used to be a 9B lathe. We can put these to use to cut metric threads. One of them is a little bit more complicated than the other, but you may be able to get more metric threads out of that. And the other one is super easy, and you can get a decent amount of them out of that. So let's come over here on the table. We'll show you what we're talking about with this nut, and we'll go through the math of how to do this. Okay, so just to take a closer look at what we got here, that's the collar nut. Here is the collet itself. Let's get a bigger one just to make it a little bit more. Okay, so here's the main taper, which would sit into the collet chuck. When you tighten down the nut on this face, it's going to draw it in and basically, squeeze it together and grab your part. Now here's the collet nut, and if you look inside here, you'll see this little feature, kind of like looks like one single thread there. You see that? I don't know if you can tell that that's there. Now what that does is when you tighten it down, it engages this little lip. And here is the secondary taper I was talking about, that 30-degree angle in here. Alright, so when you tighten that down, that engages that lip, and it holds the collet in, so when you tighten it, everything tightens down, it pulls up, and when you unscrew it to pull the collet off, it'll automatically eject itself. So there's no pushing from the back to try to pop the collet out. Okay, so now this is a bought nut, and this is a standard plain nut. I think it'll cost you around 12 bucks. I think it's cost 12 bucks. This cost around 7 bucks plus Cyber Monday deals, 30% off or something like that. There are two types of nuts. There's a standard plain one like this, and there's also a ball bearing one, which has a bearing on the inside. They're more expensive and not much gain for what we're using it for. Now, you can make these, but you can see you have to do an angle in here, have to do this little ejector piece, and then thread it up to a shoulder. And you have to make sure that you get this angle right and all this other stuff. So you can do it, it's just a little bit more difficult. Rather than do that, we just bought this for 12 bucks. But we just have to contend with that metric thread. Now the way Southbend divides... Okay, so let's take a look at the How to Run the Lathe book real quick, because in here it shows the metric transposing gear. So right here is a 127 to 100 tooth gear. That combined with a combination of a stud gear and your tumblers in certain positions, and they gave you an extra chart. For whatever reason, this here is only for a model B or C lathe. The other chart for an A, I believe, would show you the tumbler positions. I know it happens to be 32. You have to have, for 1.5 millimeter thread, you would have to have your tumbler set at 32 threads per inch with a 48 tooth stud gear. Okay, now we can approximate this 127 tooth stud gear relatively easily. So basically, we want a gear ratio, a total gear ratio of 25.4 to 1, because they're 25.4 millimeters and an inch. Okay, so the Southbend transposing set, 127 to 100 tooth compound gear, would give you a gear ratio of 1.27. Okay, now we can approximate that by taking a 56 tooth gear here and compounding it with a 44 tooth gear. Now we would have to drill holes in this and sandwich them together to basically mate these two pieces together. We would also have to make some new bushings and some new standoffs to get this to sit in the gear train. But these two gears give us a gear ratio of 1.272727. Pretty damn good approximation of the 1.27. Now, this math here only works out for our thread, and I'm pretty sure you can use this for a bunch of other ones, since it's pretty close to the approximation of the 1.27 gear ratio. So you can probably use the Southbend gear chart and these to cut other metric threads. The only thing is I don't know how far the error would compound itself throughout those. So you can work the math on the rest of them, but this math right here is just for the 1.5 millimeter thread. So our gearing setup would be a 48 tooth stud gear, right? So we'd have a 48 tooth stud gear to our 56 tooth gear, a 44 tooth gear to the 56 tooth gear, a 4 tooth gear to a 5 tooth gear that's inside the gearbox, a 14-tooth gear to a 16-tooth gear, that's also inside the gearbox. Okay, if you do all that math out, we end up with 0.471. So that means for every turn of our workpiece, our carriage is going to move 471 thousandths of travel. So now we have to figure out what our pitch is. So our lead screw pitch is 0.125. So we take our 0.471, multiply it by 0.125, and we come out with 0.05892. Well, 0.05892, when you convert it into metric, comes out to 1.49629. So that's pretty close to 1.5 millimeters. That gives us a 0.2% error. So that's one way to do it. The only problem is as I said, is you're going to have to do some machining to the gears and some bushings and everything else, but there is an easier way to do this. Okay, so this is our easier way. So right here, okay, is our normal setup. We have a 20-tooth gear as a stud gear, and we have a 56-tooth gear as our shaft input for our gearbox. That gives us a gear ratio of 0.35714. Well, we're going to change that. We're going to replace a 20-tooth with a 54-tooth gear and the 56-tooth with an 80-tooth gear. That is going to give us a ratio of 0.675. So what does that mean to us? Well, that means our lead screw is going to be spinning faster. Well, how much faster? Well, easy way to figure that out. We take the 0.675 that we are now spinning, we divide that by 0.357, and that equals 1.89. So we're moving our lead screw 1.89 times faster in this configuration than we were in this configuration. Okay, so what does that mean for us? Well, we have an 8 TPI lead screw, okay? If we take that 8 TPI divided by our faster rotational speed, that equals 4.233. So we divide that 1 to get the pitch. Okay, that equals 0.23625. Well, 0.23625 equals 6.00075. Now, I simplified some of the numbers up here, but if you do this all by calculator, that's what you come out with. So when you change it over to millimeters, you end up with pretty much 6 millimeters. And that's about a 0.125% error. So our lead screw, basically, in this configuration, turns into a 6 millimeter lead screw. Okay? So now here's the cool thing. We can take that 6 millimeters, right? And we have over here these numbers right here are the threads per inch that are stamped on our gearbox plate. Okay? So we want to figure out what the gear ratio is to get these threads per inch. To do that, we would use the original 8 threads per inch of our lead screw to get our gear ratios. So your threads per inch, the gear ratio would equal the threads per inch divided by 8 because your lead screw is 8 threads per inch. So these are basically all your gear ratios right here for each of these individual settings on the gearbox. Now these, what is this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These 11 gearbox settings, let me zoom you out just a hair so you can see them all together. Alright, these 11 gearbox settings, when you multiply that 6 millimeter lead screw by this gear ratio, guess what? You can cut a whole bunch of metric threads here. So if you look here, so here's a bunch of common ones all set up to cut millimeter threads. So we want a 1.5 millimeter thread. So we would have to have our tumbler set to 32. 32 threads per inch. We can cut a 1.5 millimeter thread by changing out our stud gear to a 54-tooth gear, our screw gearbox input gear to an 80-tooth gear, and setting our gearbox to a 32 TPI, we can cut a pretty good approximation of a 1.5 thread. Now you can see these are all the other threads that would equal out to a millimeter thread. And this is what we can cut using just those two gears. Just these two gears here. I'm sorry, not those two. these two gears here, we can cut these, what did I say, 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. We can cut those 11 standard millimeter threads. Okay, so what we're going to do right now is we'll set up on the lathe. We'll get these the gearing in place, and we'll see if we can cut this. Okay, so here's our standard gearing arrangement, and what we're going to be doing right now is changing it. So we need to put our 80 tooth gear down here. And these are all black and oily because I use Kling brand wire rope and gear oil on these just to quiet them down a little bit. So we're going to take that one out, and we're going to take this one out. Okay, and we're also going to have to loosen this up. Whoop. Alright, so we want our 54 tooth gear here. We want that on the stud as a stud gear. And we want our 80 tooth down here, and we're going to put that back on there as the spacer. Okay, now we're going to slide this idler up. And we need this idler in place because that changes the direction to the correct way. That changes the direction of the feed. So like all gears, we want a little bit of play in them. So that's buried. We don't want it buried. We want a little bit of backlash in it. And this one, shove up. And then give it just a hair of backlash, and I'm going to tighten this banjo back down. Alright, so you can see how simple that was. That's our new gearing arrangement now. So let's throw a piece of stock in there, we'll cut it down to size, and we'll try to thread it and see what happens. Okay, so we have everything set up, and it's a regular 60-degree threading tool, just like any other threading, but the only problem I'm going to have is I cannot disengage the half nuts. So I'm going to try to just reverse the motor. I have a instant reverse motor, so I'm going to see how that works. If that doesn't work, then what I can do is leave the half nuts engaged, but disengage the tool, and then re-engage it on the way back. I don't know, we'll figure it out. So for right now, what I'm going to do is we'll just get everything comfortable like normal threading. Turn this on, and use the compound here. I'm going to just touch. So I'm going to set 0 on everything. And what I'm going to do without touching anything, we are going to engage the half nuts, and we're going to see how fast this moves. right, so that's not too bad. I can work with that. All right, so let me see here. If I can kind of measure pitch roughly. That's not deep enough. All right, so this will be our scratch pass here. Let me just reverse that out a little bit so we can get some bluing. Okay, we got some bluing on there now, so we're going to take a little bit of depth of cut and we're going to see what happens. All right, because of, yeah, we got the 1.5 pitch though, but because of, yeah, that's definitely one groove there, I got 1.5. All right, so we're going to have to pull out and then before we back up. So it's going to be a little bit tricky, but we'll take another little bit of a cut. All right, that seems to work. That seems to work pretty good. I'll go for that. If you can tell, I'm just pulling that cutter back, so I'm not dragging around the backside. And as far as the grooves go, well, I'll keep going and see what happens. Alright, let's try the nut. Well, it starts. So it's got a little bit more to go then. Well, there she is. Look at that. Alright, so we can cut metric threads. Ha ha ha! Beautiful. So now we know everything works. Just give it a little cleaning. And on the back side here. I really should blow that off. I just don't want to start up my air compressor, but no wiggle. Look at that. Alright, so metric threading on an Imperial lathe. It works. So once that stock comes in, we'll start working on the body of the chuck and get this project up and going. Thanks for watching.